Hello, you're welcome. All right, so we are gonna be looking at measurement and unit in this tutorial. Okay, so now what is measurement? Okay, so measurement in physics is the act of finding the size of a physical quantity. All right, so now measurement is very important. Okay, very important in physics. Why? Because every laboratory procedure you ever take, okay, you undertake, definitely will require measurement. Okay, so definitely you want to find the size of some physical quantities in the laboratory, okay, for some experimental procedures. So that act of actually finding the size of a physical quantity is what is regarded as measurement. Okay, so now question is, what's a physical quantity, or what are physical quantities? Now, physical quantities are quantities that can be measured. Okay, any quantity that can be measured. Let's say you're conducting an experiment, then you need to, or that experiment requires you to measure mass. Mass is a physical quantity. Okay, so it it might also be length, it might be time. All those are physical quantities. So once a quantity that can be measured, right, such quantity is regarded as a physical quantity. All right, so now let's look at the classes of physical quantities. Now, there are physical quantities are divided into three classes, namely, we have the fundamental quantities, we have the derived quantities, and of course, we have vectors and scalars. Right. So now, vectors and scalars is actually a topic on its own, which we are going to treat, okay, subsequently in the series of these videos. So but here we're gonna be looking at basically the fundamental quantities and the derived quantities. Okay, so we start with the fundamental quantities. So what are fundamental quantities? As the name implies, okay, they are fundamental. Now, what are they? Fundamental quantities are quantities that provide the basic unit of measurement. All right, fundamental quantities form the foundation in which other quantities derive their definition from. So they are the basic, they actually form the core foundation, okay, that give rise to other quantities known as the derived quantities. So they actually provide the basic unit of measurement. So that is why they are called fundamental quantities. And another thing you should know about fundamental quantities is that, okay, they form the core foundation of all the formula that you will ever encounter in physics. So invariably, practically all the formulas you will ever use or you will see in physics, okay, they are being gotten from fundamental quantities. You can trace them back, okay, to a particular one or two fundamental quantities, and that is why you should know all the fundamental quantities in physics. There are seven of them, and of course I'll be listing them out. Okay, so all fundamental quantities in physics are listed below. Okay, then we have the mass. Of course, I'm going to be this one at M2 as a symbol of mass here: length, time, temperature, electric current, amount of a substance, luminous intensity. So these are fundamental quantities in physics. Okay, so there are seven of them, so you have to take your time to know them. Just make sure that you'll be able to remember the seven fundamental quantities. All right, so now we now talk about the derived quantities, and of course, as the name implies, every derived quantities is being derived from the fundamental quantities. Okay, now derived quantities are quantities gotten by combining two or more fundamental quantities, okay, in a formula. And let's look at some example. let's let's look at speed. Speed is a derived quantity. Why? Because it's been derived from distance all over time. Okay, so of course distance is measured in length. Okay, distance between 2 points is measured, okay, by the length between those 2 points. So distance is also length all over time, okay, which of course by symbol, that's L divided by T. Okay, so velocity is still a derived quantity. In the case of velocity, we are looking at displacement all over time. Now speed and velocity, they are the same. Okay, why? Because both distance and displacement, they are being measured based on the length. Their magnitude is based on the length, okay, between those 2 points. But the difference between distance and displacement here is the fact that displacement has a specified direction, okay, it's a vector quantity, while speed is a scalar quantity. All right, so now acceleration is being derived from the formula velocity all over time. When you divide velocity by time, you have acceleration. And of course, here by formula, since we already know that velocity is equal to length all over t, okay, then I now divide by another time t. So that gives me the formula of acceleration to be equal to length divided by time square, L all over t square. Okay, so please take note of that. Then you now have force. Force is actually a product of mass times acceleration. A product of mass times, and these are derived quantity. Okay, so a whole lot. So just any formula you can think of, and this for a physics student, you should remember formula, right? So if you could remember the formula of that particular quantity, then you know the fundamental quantity that that formula is actually being made up of, right? So now we now talk about dimension. Okay, so dimension is really very crucial, right? So in dimension, what we are looking at is the size of a quantity, okay, measured from the fundamental quantity which make up its formula. So invariably now, when you are being asked to express a particular quantity in dimension, just all you just need to do is just to translate that quantity or whatever formula it is, okay, by the symbols of the fundamental quantity that make up that particular formula or that quantity, if that's actually okay. Of course, I will explain. Now in dimension, we use symbols of fundamental quantities, okay, in an uppercase letter. For example, if I want to express any quantity, derived quantity in a dimension, if that quantity contains mass, I'll be using capital letter M to represent masses. If it contains length, I'll be using capital letter L to represent length. If it contains time, I will be using capital letter T to represent, okay, time. And the after, okay, using this symbols or the alphabet, okay, then whatever you have as your answer, probably the formula should be in an exponential form. So the answer is not we don't keep our answer in fractions, okay. The answer is not left in fraction, but it should be in an exponential form. Then I think example will actually make more sense. Okay, let's look at example here. Express the following in dimension. These are the following quantity. Okay, so we're looking at velocity, acceleration, and force. So I'm starting with velocity, so I will go to my board. Okay, so I hope you're with me. Yeah, so I'm looking at velocity, okay, which already we know velocity is equal to displacement all over time, and also displacement is measured in length, right? So in dimension, we use capital letter L to represent length, then all over time, capital letter T. So we don't keep this answer. I'm not going to keep this answer in fraction, but rather in an indecimal or exponential form. How do I do that? I'll have to take T, all right, to the numerator. Okay, I have to invert T, find the reciprocal of T. So if T is being taken to the numerator, it becomes, remember, reciprocal, it becomes T raised power minus 1, all right? So that is the dimension of velocity. Then of course, let's look at acceleration, the dimension of acceleration. Don't forget that as acceleration is given as velocity, all right, all over time, all right. So by extension, we already know that velocity is L over LT raised power minus 1. We've already gotten this. Then divided by time again. All right, so you know what happens here. This time we're still gonna go up, so that I'm gonna be having LT raised power minus 1, then times T raised power minus 1. All right, so now in indices, you know very well that if you do T raised power minus 1 times T raised power minus 1, you end up having T raised power minus 2. So that is the dimension of acceleration. All right, so what's the next? The next is this is number one. Number two part of the question. Then number three, the dimension of force. All right. Okay, so by formula we already know that force is equal to mass times acceleration. So by dimension, the dimension of mass is capital letter M. You know that already, and the dimension of acceleration has already been given here. That's LT as the power of minus 2. All right, number four. I think what we have there was the dimension of work. Work is, of course, is giving us force times distance. Okay, perhaps I'll use D. Let me use D. All right, so force, I have already expressed force in the dimension. That's MLT raised power minus 2. All right, then times distance, which of course is T measured in length, L. Okay, so if I should do this, that's gonna be ML. L times L is gonna give me L squared. All right, then T raised to the power of minus 2. Okay, so it's just as simple as that. Once all you need to know the formula, then you can transform it into a dimension. I can still go on. Okay, let's look at formula that we know in physics. Let's look at power. Of course, power is energy or work divided by time, right? Work all over time. Right, so now in a case like this, I already have, okay, I've evaluated for work. That's ml squared t raised to the power minus 2. All right, so divided by time, which of course is capital 30. You know very well that this capital 30 will go up to become t raised to the power minus 1, right? So what you're going to be having is ml squared t raised to the power minus 2, all right, then times t raised to the power minus 1. So if we should do this now, this is going to be ml squared t raised to the power minus 3. Minus 2 minus 1, that's minus 3. So that is dimension. Okay, so I hope that is well understood. We can still look at more questions, okay, but let's proceed. All right, here we go. So now let's look at units of measurement. All quantities have units for their measurement. Okay, now in physics, the general accepted unit of measurement is called the System International, which of course is SI unit. Okay, so definitely anytime you actually take measurements, okay, there's always a unit for that measurement. Every quantity have units for its measurement. How do I know? Anytime someone actually takes this measurement and say that what he got is 20, I can't tell what he measured unless he told me. But if the person actually put meter, okay, after the 20, I will know very well that, okay, by the unit, okay, that's attached to this magnitude, to this quantity, I know very well that what the person measured is what length. All right, so every quantity has every quantity have a unit of measurement. So now we're going to be looking at, we'll start with basically start with the fundamental quantities and their unit. If I will have a table here, yes, I have a table. So all the fundamental quantities we listed, the 7 fundamental quantities we listed, we're going to be looking at their units. Okay, for length is measured in meters, so please take note of that. That doesn't mean there are no other unit for length. That is what is called SI unit, System International. So meter is accepted as the System International unit for length. Mass we have kilograms. Time we have seconds. Of course, this is the abbreviation for kilogram, kg, seconds, x. Current we have ampere, A. Temperature we have degrees. This is Kelvin. Okay, please take note. The SI unit of temperature is Kelvin, so please do some correction here. Amount of a substance is mole. Luminous intensity is candela. All right, so we'll now go to the derived quantities and look at their units. Okay, so here we have velocity as a derived quantity, which we know that velocity is always given as displacement all over time. Okay, so that's going to be displacement is measured in meter, that's length, all over time seconds. So the SI unit of velocity is meter per second. Acceleration, we know that, okay, it's always given as length all over time square. We have already done that. So for acceleration, we have meter all over second square. Force, Now, some of the SI unit, that's why it is called SI unit, okay, is not actually gotten from the derived unit, but rather is actually named after a particular scientist or physicist, okay, that probably contributed to the development of that particular quantity, right, for force. All right, normally if I should have go by the derived unit of force, I would have okay, so that by derived unit of force, since force is equal to mass times acceleration. So by derived unit of force, I will simply say that it's gonna be kg, which is for mass, then acceleration, that's meter. This is actually the derived unit for force. But by SI units, okay, SI units is in Newton, all right. So by SI unit rather uses Newton, of course, capital letter N. Okay, so I hope that is one. So work, the same happens with work, which is first and this, but instead of probably Newton meter, here work is measured in joule, power is measured in watt, density kilogram per meter square. So of course, I believe that by the time you go through all these particular quantities, these formulas, you get to know their derived units. So let's proceed. So we'll now talk about submultiples and multiples of units. Okay, submultiples and the multiples of a unit. All right, so now there's something you should we've already talked about it. Okay, we know that for SI unit, there's a particular unit is actually designated for SI unit of a particular quantity. That doesn't mean that there are no other units. Okay, so for an SI unit, there might be higher units known as multiple units, which is greater than the SI unit, and there might be lower unit which is known as submultiples. Okay, so now we see that smaller factors of a unit are called the submultiples. All right, so when the smaller factors of a particular unit is called a submultiple. For example, I have meter. Okay, below meter we have centimeter, we have decimeter, have millimeter, right? Those are smaller factors, and you should know how to convert all those smaller factors, okay, to the actual SI unit. Why? Because some questions in physics require conversion. All right, so let's look at some table now. Submultiples and their conversion factor. Let's look at micro. When unit is a micro, okay, that means that unit, for you to convert that unit, you have to divide by 1 million. Okay, micro is always divided by 1 all over 1 million. Okay, so I think that should be 1 0 added to this, but by standard form, that is going to be 1 times 10 raised power minus 6. For example, 2 micrometer, if I want to convert 2 micrometer to meter, I have to divide 2 by 1 million, or I multiply the 2 by 10 raised power minus 6. Milli is divided by 1000. If you want to convert milli, you divide by 1000. Okay, if you or you multiply by 10 raised power minus 3. If you want to convert centi, you divide by 100. If you want to convert deci, you divide by 10. I think we will definitely look at examples. Okay, now these are multiples higher. Okay, multiples are the larger or higher factors of a unit. The table below, okay, shows some multiples factor. So we start with kilo. Kilo, in multiples you are multiplying, right? So for example, if you want to convert kilometer to meter, you multiply by 1000. Mega, you multiply by 1 million. Then giga, you multiply by 100 million. All right, so now you should actually take note of this. Converting is vice versa. Okay, if you are converting from a submultiples to the unit, you divide. All right, but if you are going back, let's say you are converting that unit to the submultiples, okay, you multiply. I think example will illustrate this better. Now let's look at some examples here on the screen, okay, that will let's do justice to these questions. Here we have the question it goes this way: convert the following units to meters. So here I have 2 millimeter, 5 centimeter, 10 kilometers. So with what I've given you, this will be so simple, right? So let's start with the very first. Here, okay, 20 millimeter. How do we convert 20 millimeter? So of course you know milli, remember, okay, we divide by 1000. So 20 millimeters, same thing as 20 divided by 1000. And when you divide 20 by 1000, you're gonna have 0.02. So that will be 0.02 meter. All right, so what's the next question? Here we have 5 centimeter. All right, 5 cm. To meter, remember, you just need to divide, converting cm to meter, you divide by 100. That is, that's, what about, is that 5? Okay, please, pardon me. All right, 5 centimeter. So in this case now, that's going to be 5 divided by 100, which of course should be 0.05, right? 0.05 meter. Then what do we have next? Okay, 10 kilometer. All right, 10 kilometer multiples. Remember, in multiples you multiply, that will be 10 times 1000 kilo. You multiply by 1000, that's gonna give us 10,000 meter. All right, and then let's proceed. We have next. All right, 3 centimeters, 3 cm cube, cm square, please pardon me. So now that is okay. I think this is kind of somehow, it's not complex, but it's more complex than the others. Okay, I think this is a part of the question. This B, C, and here we have the D. All right, so now if we are converting centimeter cube to meters, centimeter square to meter square, simple. The first thing you need to do is to actually convert the cm to meter, then you now square it. Simple. So I have to convert the cm to meter. Of course, that will divide by 100. That is the first thing you need to do. Then, so for square, okay, you have to square your answer. So that's gonna be equal to, this is gonna be 0.03, right? Then all square, which that should give me 0.0003 meter square now. All right, so here we go. Then we now have 10 centimeters cube. So this time around, that is being cube, centimeters cube. So first you need to convert the 10 to, okay, to meter, 10 centimeter to meter, then you now cube it. So that's gonna give me 0.1, right? All cube, which should be 0.001. Okay, so I think I made a mistake in this one. This my multiplication here. All right, this is 0.009 rather. Okay, because I have to, that's 3 square here. That's okay. So it's as simple as that. I hope that is well understood. All right, so back to my slide. Let's proceed. So having gotten to know the quantities, dimension, their units, so we'll now talk about measuring instrument, because every measurement you need measuring instrument, okay, to actually undertake any all measurement, okay, in physics. Okay, a particular quantity and have its measuring instrument. So we're going to start with length, the measuring instrument of length. Okay, now there are different measuring instruments of length, and the instrument you choose, or the instrument, okay, that is selected depends on the precision of the length you want to measure. Is it a long length that you probably that you need to, that require you measuring up to kilometers or acres, right? Then definitely you need a measuring tape. But if it's just a very short distance, okay, you need a meter rule. As you can see here, this is a meter rule. Okay, now there's one thing about a meter rule is this, the precision of a meter rule, which is something as accuracy. Anytime you hear of precision, it's talking about accuracy, okay, or even the least error. It means the same thing. Of a meter rule is always 0.1. How do I get to know the precision or the accuracy? The highest accuracy a meter rule will give you, okay, or the least error is best is this the value for the smallest division of that meter rule gives you the precision. Okay, let's take an example from 1 to 2. You discover that between 1 to 2, each small division, okay, is 0.1. From 1, the next small division is 1.1, 1.2. So it is increasing by 0.1. Okay, so the least division that you have in the meter rule is in this meter rule. Of course, in every meter is always in 0.1. So that is the least error you will get, and that is the precision or the accuracy. So if you want any accuracy that will measure anything lower, okay, more accuracy, then you don't need a meter rule for it. But for a meter rule, then there's nothing to. If you look at another diagram here, I have meter rule that is being actually okay, that I have, okay, in which I have 3 students taking reading from this meter rule. Okay, there's one error that is actually common to reading that is taken from a meter rule. What is that error? That error is known as Pararas error. Okay, Pararas error is caused when you want to take reading from a meter rule. You don't look directly down, vertically down, okay, to the meter rule, but rather you look from a slant angle. Okay, by looking at the meter at a slant angle, you might end up missing some, okay, some division, some point. So as you can see now, the only student that actually got the reading correctly is the student B. Okay, so student B is just right, okay, because he got that reading. The reading was supposed to be 20, and what he got was 20. But student C actually got a higher reading. Why? Because, okay, he slants his head at a point, okay, that made him to have his reading becomes 21.5. So such error, okay, in physics measurement or measuring from meter rule is known as Pararas error. Okay, so please take note of that. Now there's another length measuring instrument. This time around, this one is called a vernier caliper. A vernier caliper is basically used to measure the internal and external diameter of a hollow object. As you can see here, this person is actually using a vernier caliper to measure a ball bearing, okay, the external diameter of a ball bearing. So if he needs to actually measure the internal diameter, all you need to do is to clip inside the internal diameter of the ball bearing, all right, and you can measure it. So now this is the schematic diagram of a vernier caliper, all right, which have number one, the vernier scale. So the one inside, this is the vernier scale, okay. Then you now have the movable scale. Oh please, sorry, the main scale, okay. The main scale is the one inside, okay, and it is actually being okay, it is outside the main scale or covering the main scale becomes the vernier scale, and the vernier scale is slidable. You can slide it to clip that particular object you wish to measure, as you can see here. All right, so 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 that means taking measurement from a vernier caliper, all right, require the measurement, the reading, okay, is taken from both from the main scale, okay, which takes the main reading, right, then of course the vernier scale that takes the some you know, some units or decimal units of the reading. Okay, I think there's a question here that I need to, that will help me illustrate this. All right, so now the question goes like this: the length of a piece of glass block was measured by means of a vernier caliper shown above. So this is the reading. This is the vernier caliper. The length of the glass block is. So now how do I take this reading? Simple. Both from the main scale and the vernier scale. All right. if I should take the reading from the main scale, you discover that what I have here, this is 1. This is 1, 2, 3. The main scale is 3. Then, but this is the place where the vernier scale stop. The vernier scale stop after 1.6 because this is 1.5, right? Quite well. It's 1.5. So 1.5, 1.6. Okay. So then there's some small fraction. It was not directly at 1.6. Okay. So it is just a little bit, okay, beyond 1.6. So first of all, if I want to take that reading, okay, of course, the reading, if I want to take the reading, first of all, I will read off from the main scale. Then I'll now read from the vernier. Right? All right. So the main scale already is giving me 1.6, right? Yes. Then plus some division, small division that I need to take from the vernier scale. All right. So this small division after 1.6 is what I will take from the vernier scale. How will I get it? I will get it after counting the number of division to the point where both the main scale coincide with the vernier scale. As you can see, that is at this point too. That's where it coincides. So if I count the number of division of the vernier scale to that point, is you have how many division? 1, 2, 3, 4. 4 division. And please take note, this I've already told you that for a meter rule, the precision of a meter rule is 0.1, which simply means that the smallest division in a meter rule is just 0.1 unit. But for a vernier caliper, okay, the precision is 0.01. That means each of this small division, the smallest division, of course, you get the smallest division from the vernier. Each of the small division, each of them is 0.01. So since there are 4 of them, so let's go back to my reading. So I'm going to have 4 division in which each one is 0.01. All right, so in this case now I'm gonna be having 1.6, okay, plus that should be 0.04. So this will not be my reading, okay. Of course it's in millimeter, right? That's gonna be 1.64. So that is how we take reading from a vernier calipers. All right, so the next length measuring instrument is known as micrometer screw gauge. Micrometer screw gauge. Now, okay, what kind of length do we measure with micrometer screw gauge? Now, very small, tiny amount of length, like the diameter of a wire. Of course, you know a wire has a very tiny diameter. Yes, that is, it will give you a micrometer screw gauge can measure such diameter with a higher accuracy, okay, compared to other length measuring instruments. It can also use it to measure the thickness of a paper, of course. And this, of course, look at you just the same way you use vernier caliper to clip, okay, the object you want to measure. That's how you also clip using micrometer screw gauge. So now this is the schematic diagram. Okay, it's called screw. Of course, you screw it until you screw the object. Okay, you screw it tightly, okay, on the object. So now here we have the main scale as usual. Then of course the rotating scale, you have the rotating scale because you have to screw. So that means, as we already discussed, okay, from the when we talked about the vernier caliper, okay, the same thing goes with a micrometer screw gauge. The reading is actually gotten by combining, adding the main scale and the rotating scale. All right, so now I think this diagram will actually help us illustrate, because sometimes in most cases in the exam you'll be given a diagram, you'll be asked to take the reading here in this reading now. So what's the reading of this? As you can see here, okay, the main scale is giving us 5.5. Of course this is 5, this is 5.5, and there are some, okay, tiny division, okay. So the rotating scale didn't actually stop at 5.5. There are some little gap. So how do I get that little gap? I get that little gap from the rotating scale, and we get it at the point where the rotating, by counting the number of division, okay, to the point where the main scale actually coincide with the rotating scale. So I say this is at this point. This is 30 quite well, and then of course the next division is 31, right? So that means the rotating scale is 31. So the same reading goes for micrometer screw gauge. So if I'm taking reading from the micrometer screw gauge, right, I will still go by adding the reading of the main scale plus the rotating scale. All right, from what we have there, the main scale gave me 5.5, and the rotating scale is 31. Okay, division. Please, you need to ask because each division should have a particular value, and that is it for a micrometer screw gauge. Is still the precision of a micrometer screw gauge is 0.01. That means each division is 0.01. So since we are having 31 division, okay, that's going to be 31 times 0.01. So this should give me 5.5, then plus 0.31, right? Okay, so if we should do this, that should be 5.81, and it's in millimeter, I believe. Yes, it's in millimeter. Okay, so that is how we take our reading. Let's proceed. Let's proceed. Okay, so now I think at this now we are going to be solving questions, a lot of questions. Okay, here I have the very first question. Here it goes this way: the new power station measures their power output in gigawatts. The power of the electric kettle is measured in kilowatt. How many kilowatt are there in gigawatt? Okay, remember this is conversion. This is conversion. Let's see how we do that. Right, of course I've already given you the converting units for converting factors, excuse me, for both the multiple and the submultiple. So in this case now, so the new power station measured their power in gigawatts. Okay, so we are looking for how many kilowatt and gigawatt. Now the formula for our conversion is always from we converted from kilowatt to uh, watts, which of course the SI unit. Okay, so there is no direct conversion from gigawatt to kilowatt. So if I want to do this, so the first thing I'm going to do is to convert this gigawatt to watt. So it will be easy enough for me to move from watt to kilowatt. So how do we convert gigawatts to watt? All right. Okay, so how many of the, okay, so how do we convert 1 gigawatt? Of course 1 gigawatt is 100 million watts, or 10 raised power 9. Let me just do that. 10 raised power 9 watt. So now 10 raised power 1 watt. Now I want to convert watt now to kilowatt. Remember, if you want to convert kilowatt to watt, you multiply by 1000. Already, you know that already. Okay, so what if you want to convert if you want to convert from kilowatt to watt, you multiply by 1000. What if you want to convert from watts to kilowatt, you now divide by 1000. It's vice versa. Okay, so that's going to be 10 raised power 9, then divided by 1000. That is divided by 10 raised power 3, right? Divided by 1000, which now in kilowatt. So of course when you divide 10 raised power 9, which of course is 990, okay, this 30 will cancel 30 out of 90, so you have 60. That will give you 10 raised power 6. So 10 raised power 6 kilowatt, right? Okay, and of course that's the megawatt. 10 raised power 6 is 1 million watt. Am I correct? Okay, nope. Okay, 10 raised power 9. Okay, 10 raised power 6 kilowatt. Please pardon me. Okay, so that'll be 10 raised to the power 6 kilowatt. All right, so let's move forward. The dimension of universal gravitational constant is. Okay, so we talked about dimension. Let's flow. It is easy. In dimension, once you know the formula of that particular quantity, you can always convert it to dimension. Now for universal gravitational constant, is gotten from the Newton's formula of universal gravitation, which of course you should know. Okay, that's one thing about dimension. You should be very conversant with formula. If you don't know the formula, you can't convert it to a dimension. All right, so Newton's law of universal gravitation actually give us the formula for gravitational force, which is Gm1 m2 all over r square. So this is the G here is the universal gravitational constant, and that is what we want to express in dimension. So I have to make it the subject. Making the subject, you know what I would do? I have to cross multiply, right? That's going to be fr square, then divided by m1 m2. So having gotten the formula, now let's take this to a dimension. Of course, you know F in dimension is force in dimension. We've done this already. That is mass times acceleration mlt raised power minus 2. This arrow here represents distance, okay? Distance between the two masses. And of course, that is distance is the dimension of distance, of course, is L. That's L square here. This m, that's mass, okay? M times m, that's gonna be m square. Okay, of course, m cancels itself, cancels m square. I'll just have m in the denominator. And of course, you know very well that I need to take this m up to give me m raised power minus 1. So if I take it up, that's going to be m raised power minus 1. Okay, then t raised to the power of minus 2, then L square. So that is the dimension of the universal gravitational constant. So m raised power minus 1, L cubed, t raised power minus 2. That's a part of the question. Okay, so which of the following unit is equivalent to what? Okay, so if you can get it in dimension or in formula, you can get it in units. Let's see. We've done that before. Of course, we did that. I can also do it again. For watt, no, watt is for power, right? That is work all over time, which by dimension, right? We know work is okay. We did work, and that's gonna be m L square t raised power minus 2. Yep, if I'm not mistaken, then t. So this gives me m L square, right? Then of course, if this goes, this t raised power minus 1, minus 2 minus 1, that's minus 3. So this is in dimension, but in units, let's put it in units. The SI unit of mass is kilograms. SI unit of length is meter square. Then time is seconds. SI unit of length is meter, then L square, that's meter square, and then time is seconds. That's seconds raised to power minus 3. So kg m square s raised to power minus 3, that is our answer. All right, kg m square s raised to power minus 3, that's B, part of the question, that's B. Okay, so here I have another question. It goes like this. At what respective value of A, B, and C would the unit of work, the joule, be dimensionally similar? Okay, so, and of course, m raised to power A, L raised to power B, T raised to power C. So we are looking for work, which, okay, so at what unit, at what value of A, all right, would this dimension be a dimension of work? That's just what the question is asking. So the question is, what's the dimension of work? So already we dimension of work, we know that is just ml square t raised power minus 2, right? So in that case, now A is the power of m. The power of m there is 1. B is the power of L, which is 2. C is the power of 2, which of T, which is minus 2. Okay, let's proceed. The period P of a simple pendulum is a time for one complete swing. How does P depend on the mass m of the bulb, the length L of the string, and the acceleration to gravity? Okay, I think this is dimension. So okay, so the period of P. So the question, how does P depend? Invariably what they are looking for is the dimension of the period, okay, and they call it P, right? So let's do that. So of course the period of a simple pendulum, if you know by formula, is given as 2 pi the square root of L all over G. So this is going to be P, right? It's equal to, now this 2 pi I don't need to, okay, simply it's a constant. But of course here for this is L length, okay, so it's gonna be still in dimension is length. Acceleration due to gravity here, okay, is meter per second square. That's acceleration, okay. So in dimension, of course, you know that for that one that's ml, right, t raised power of minus 2, right? So L cancels L, so I have the period being equal to 2 pi. Okay, this is a constant. I don't really need it, but I will take it out. Okay, but in this case now t raised power minus is reciprocal, so the t comes up, that becomes t square. Okay. Making, what am I doing? There's no mass in acceleration. Please pardon me. Pardon my mistake. So what I have here is just L, okay? That's supposed to be L t raised power minus 2, which L have actually cancelled L, okay? So t actually comes up. That's t all over 1, okay? Reciprocal. So which of course is a constant. I don't need it, okay? It's just in dimension. I don't need to include the constant. So it simply means that the period, okay, becomes just the square root of t square. So period square root of t square is just t. So period is correct. So this shows that, okay, after you must have evaluated this formula, the period, which of course is still t, all right, because of we know very well that period, okay, in physics we still capital letter T to represent it, which of course is the dimension of time. Okay, if that actually makes sense, but it should make sense. All right, okay, so that is it for, we're still gonna look at more examination question, okay, we'll still look at more. So see you in the next video. Thank you very much.